Deep in the heart of Anhui province in eastern China, inside a building the size of an aircraft hangar, a machine sits at the center of a circular chamber and burns at 150 million degrees. That is 10 times hotter than the core of the sun. The walls of the chamber never touch the fire. Nothing touches the fire. The fire floats inside a magnetic field that holds it in place while it burns. A beautiful nightmare for physicists and engineers. The challenge: build a machine that can contain a star, sustain it, and extract its energy without the star destroying everything around it. This is the EAST reactor, the experimental advanced superconducting tokamak, China's artificial sun. In 2000, the mobilization began at the Hefei Institutes of Physical Science. Over 600 scientists and engineers were assembled. Hundreds of specialized manufacturing facilities across China were commissioned to build components that had never been manufactured before in the history of industry. The construction of the reactor chamber itself required welding techniques that did not exist at the time the project was approved. The clock starts now. We build what we do not yet know how to build, and we learn how to build it as we build it. The machine at the center of everything is a tokamak. The name comes from a Russian acronym describing its shape: a toroidal chamber with magnetic coils. A hollow metal donut, roughly 11 meters across and 4 meters tall, surrounded by the most powerful superconducting magnets ever assembled in a single machine. The donut is the reactor vessel. The plasma, the superheated gas that burns at stellar temperatures, lives inside the donut. The magnets create the invisible cage that holds the plasma away from the vessel walls. Without the magnetic cage, the plasma would touch the vessel wall in a fraction of a second, and the temperature would drop instantly from 150 million degrees to near zero. The reaction would stop. The star would go out. Building the reactor vessel requires welding stainless steel plates to tolerances measured in fractions of a millimeter across a curved surface 11 meters wide. Thermal expansion during welding distorts the metal. Every weld sequence is designed to minimize distortion by alternating heat input around the full circumference of the vessel. Teams of welders work simultaneously at multiple points on the vessel, their sequences choreographed so that the heat they add in one location is counteracted by the contraction occurring at the location where welding finished moments before. The finished vessel must hold a vacuum 10 times more complete than the vacuum of outer space. A single small porosity in a single weld will destroy the vacuum. Every weld is inspected by X-ray and ultrasonic testing before the next weld begins. Weakness is not an option. The superconducting magnet coils that surround the vessel are the most technically demanding components in the machine. Superconductivity requires cooling the coil conductors to negative 269 degrees Celsius, just 4 degrees above absolute zero, the coldest temperature achievable in nature. At that temperature, the electrical resistance of the conductor drops to zero. Current flows without loss. The magnetic field the coils produce is stronger than any electromagnet that operates at room temperature. The coil conductors are made from niobium titanium alloy wires, each one thinner than a human hair, wound together in cables, formed into the rectangular cross-section of the coil, and then encased in a stainless steel jacket that contains the liquid helium cooling system. The coils are assembled in a clean room environment where the temperature is controlled and the air is filtered to remove particles that could contaminate the superconducting surfaces. A single contamination event can degrade the performance of a coil permanently. Every coil is tested at full operating current before installation. The cryogenic system that maintains the magnets at operating temperature is itself a major engineering project. Liquid helium at 4 degrees above absolute zero must be circulated continuously through the magnet coil system. The helium is cooled in a dedicated cryoplant using a multi-stage refrigeration process that starts at room temperature and steps down through progressively lower temperatures using a series of heat exchangers and expansion stages. The cryoplant consumes more electricity than a small town. The piping that carries the cold helium from the plant to the magnets is insulated by a vacuum jacket that prevents heat from the surrounding environment from reaching the cold fluid inside. Where the piping passes through structures, flexible bellows accommodate thermal expansion and contraction without transmitting stress to the piping system. The cold fluid inside the pipe contracts by measurable amounts as it cools from room temperature to operating temperature. Everything in the cryogenic system is designed for the dimensional changes that this cooling produces. We build the machine in modules assembled in sequence. The lower half of the vessel is placed first, supported on a rigid base structure that will carry the full weight of the assembled machine and the forces that the magnets generate during operation. The magnet coils are lowered into position around the lower vessel, half one by one. Each coil weighs several tons and must be positioned to millimeter accuracy relative to the vessel's centerline. A laser tracking system with targets mounted on the vessel and the coil forms measures the position of each coil in 3 dimensions as it is lowered. The crane operator adjusts position based on the laser readings. The coil lands in its final position and is bolted to the support structure. Then the next coil arrives. Then the upper half of the vessel is lowered onto the lower half. The two halves are welded together at the mid-plane joint, while the finished lower structure holds everything in place below. The plasma heating systems are installed in ports that penetrate the vessel wall. Neutral beam injectors fire streams of high-energy particles through these ports into the plasma, adding energy that raises the plasma temperature. Radio frequency heating systems broadcast electromagnetic waves at frequencies that couple to the natural resonance of the plasma, driving the ions to higher energies. The combination of these heating methods brings the plasma from its initial temperature at breakdown to the target temperature of 150 million degrees over a period of seconds. At 150 million degrees, the hydrogen isotopes in the plasma begin to fuse. Deuterium and tritium nuclei collide and combine. The reaction produces helium and releases a high-energy neutron. The neutron carries the fusion energy out of the plasma and into the surrounding structure, where it can be captured as heat. This is the principle. This is what the machine is built to prove. The critical obstacle comes during the first plasma tests at high magnetic field. Midway through a sustained plasma discharge, an arc fault develops in the power supply system feeding one of the poloidal field coils. The fault deposits energy into the coil faster than the quench protection system can respond. The coil warms above its superconducting transition temperature. Suddenly, it is no longer superconducting. The resistance reappears. The stored magnetic energy begins converting to heat inside the conductor. We have milliseconds to dump the stored energy into the external dump resistors before the conductor temperature rises to a level that damages the insulation. The protection system fires. The energy transfers to the resistors. The coil temperature peaks and begins to fall. The plasma goes out as the magnetic field collapses. The discharge is lost, but the coil survives. The quench protection system performed exactly as designed. The discharge is over, but nothing is broken. Cheering. The East reactor holds the record for the longest sustained plasma discharge at the highest plasma temperature ever achieved. In January 2022, the reactor maintained aplasma at 120 million degrees for over 1,000 seconds. 17 minutes of artificial stellar fire, held in a magnetic bottle, consuming no fuel that leaves carbon in the atmosphere, producing no long-lived radioactive waste, contained within a chamber the size of a small building in a research facility in Anhui Province. The machines that will extract usable electricity from fusion reactions do not exist yet. They are being designed now by teams working from the data that East produces. The reactor is not a power plant. It is the proof that a power plant is physically possible. Scientists and engineers in 30 countries are now building or planning tokamak reactors based on the techniques developed at East and at other fusion research centers around the world. The data from 1,000 seconds of plasma at 120 million degrees will be analyzed for years. Every measurement tells the designers of the next generation of machines something they could not calculate from theory alone. A star that burns in Anhui for 17 minutes leaves behind information that shortens the time to the machine that will burn for 17 years. If projects like this one move you, subscribe so you never miss what we cover next. Drop a comment and tell us where in the world you're watching from. The diagnostic systems that measure the plasma during a discharge are the most sensitive instruments ever installed in a single facility. Hundreds of sensors are positioned on the inside wall of the vacuum vessel, measuring plasma temperature, density, pressure, and positioned 10,000 times per second. The measurements must be made without disturbing the plasma. Many of the sensors work by detecting the light and radiation that the plasma emits, analyzing its spectrum and intensity to infer the physical conditions inside. Others detect the magnetic fields produced by the plasma currents. The data from all sensors flows simultaneously to a control system that uses it to adjust the heating power, the magnetic field configuration, and the plasma boundary position in real time during the discharge. The control system makes thousands of adjustments per second. The plasma responds to each adjustment within milliseconds. The discharge is not a passive event watched from the outside. It is an active process, managed continuously by a system that reads the plasma and responds to it faster than any human operator could. The vacuum inside the reactor vessel must be maintained at a pressure lower than the pressure of interstellar space. Any gas molecule remaining in the vessel when the discharge begins will be ionized by the plasma and will contaminate it, cooling it and terminating the discharge prematurely. The vessel is pumped down over several days before each experimental campaign begins. Turbomolecular pumps and cryopumps work in series to remove gas molecule by molecule from the vessel interior. The walls of the vessel are baked at elevated temperature for days before pumping begins, driving absorbed gas molecules out of the metal surface into the vacuum where the pumps can remove them. The process is called conditioning the vessel. A well-conditioned vessel holds its vacuum longer and produces cleaner, hotter plasmas. The team at East has spent years learning how to condition the vessel to the point where it holds discharges that no earlier tokamak could sustain. The tokamak building that houses East is engineered to isolate the machine from ground vibration. The foundation under the machine is a massive reinforced concrete inertia block that sits on vibration isolation bearings, decoupling the machine from the movement of the surrounding building and the ground beneath it. Heavy trucks passing on the road outside would otherwise transmit vibrations through the ground into the vessel, perturbing the plasma position by fractions of a millimeter. Fractions of a millimeter matter when the plasma must be held away from the vessel wall by a gap of only centimeters at operating temperature. The isolation system reduces external vibration transmission to the machine by a factor of more than 100. The machine sits in effective stillness even when the world outside moves. The fuel for the plasma is deuterium, a naturally occurring isotope of hydrogen that makes up roughly 1 in every 6,000 hydrogen atoms in ordinary water. The deuterium in 1 liter of seawater contains enough fusion fuel to produce the energy equivalent of 300 liters of crude oil. The fuel is delivered to the plasma through gas injection valves in the vessel wall, puffing deuterium gas into the discharge in precisely timed pulses controlled by the plasma control system. The amount delivered in each pulse is tiny. The plasma contains only a few grams of fuel at any given moment. The reaction rate at the current stage of research is far below what would be needed to produce net energy output. EAST is not yet producing net energy. It is demonstrating that the plasma conditions required for net energy production are physically achievable and technically controllable. Every second of stable plasma at 150 million degrees is a second of data that brings the net energy machine closer. This is the EAST reactor, a machine that creates conditions that exist nowhere else on Earth. A star that lives for seconds, then minutes, then eventually for the hours and days required by the power plants that will follow it. Built in Anhui, watched by 30 nations, burning at 150 million degrees. An engineering marvel inside a magnetic bottle. The neutrons that carry fusion energy out of the plasma present a long-term engineering challenge that the EAST reactor is also designed to study. High-energy fusion neutrons travel through everything. They pass through the plasma-facing components on the vessel wall, through the steel of the vessel itself, through the magnet coils, and into the surrounding biological shielding that protects the operating personnel outside. As they pass through structural materials, they knock atoms out of their lattice positions, accumulating damage that gradually changes the mechanical properties of the material. Steel becomes harder and more brittle. The changes are not visible on the surface. They accumulate invisibly in the atomic structure of the metal over years of neutron exposure. Material scientists study samples of vessel wall material removed at scheduled maintenance intervals, analyzing the changes in microstructure and mechanical properties to understand how the structural materials of a full-scale fusion power plant will age over decades of operation. The results inform the material choices for the next generation of machines, where neutron fluxes will be far higher than in EAST, and the cumulative damage will accumulate faster. The magnetic field that confines the plasma at EAST reaches magnitudes that would destroy conventional copper electromagnet coils in seconds through resistive heating. Superconducting coils carry the current without resistance and without heat generation. But the forces between the coils at these field strengths are enormous. The coils pull toward each other and push against each other simultaneously, the net force trying to collapse the magnet system inward toward the plasma axis. The structural support system that holds the coils against these forces is engineered from the same stainless steel used in the vessel construction, machined to tolerances that allow thermal contraction from room temperature to operating temperature without binding or misaligning the coil positions. Every structural component is analyzed for the combination of magnetic forces, thermal stresses, and gravity loads that it will experience during operation. The safety margins on the structural components are conservative. The machine will operate for decades. Fusion energy is the one energy source that runs on a fuel that exists everywhere, produces no carbon, leaves no long-lived radioactive materials, and cannot undergo a runaway reaction. The plasma goes out the moment the external heating is removed. There is no chain reaction to control. There is no stored fissile material that could be released in an accident. The machine requires enormous technical sophistication to operate, but the physics of it is inherently safe. EAST proves that the plasma can be ignited, controlled, and sustained. The engineers who study its data are building the machines that will prove it can power cities. The first one burns in Anhui. The ones that power the world will follow.